Cheers. Yeah, no, that's very clear. Yeah, perfect. Thanks a lot.
Thank you.
So that said, we're moving on to the last talk of this session, which is also the second talk. A pretty interesting talk, I think. It's a topic that's close to my heart. From my own work, we're looking at trying to predict the form of XANES spectra with machine learning. So we're taking the structure and going towards the spectrum. But here, this talk, it really looks like it's going to be the reverse of this problem. So being able to extract information and to analyze the experimental spectra, also using machine learning. So I'm certainly looking forward to it. I hope everyone else is. So please take it away whenever you're ready.
Okay, thank you. Dear colleagues, we would like to share the information about the route to extract local 3D atomic structure and electronic structure information from XANES, but by using not normal approaches, standard approaches, but approaches that is using machine learning algorithm. And okay, yes, and clearly it is. Oh, we could not change. Okay, and we are using machine learning, and the reason for this in many cases that now we have really big data obtained in modern large-scale facilities, and it is difficult to analyze results fast enough. And that is why, and with necessary precision, and that is why we decided to develop a route for faster elaboration of the spectrum and for faster solution of real problems that we would like to solve. And our talk will be organized in several parts. First, we discuss methodology of machine learning application for XANES analysis. Then we will share several case studies we have done. Then we will discuss the reduction of time for this process, and this is clearly, we will discuss also a very important part of this approach in the selection of descriptors, and then finally conclusions and our outlook, and we will discuss slightly what we would like to do next. Okay, methodology. In many cases still now, the XANES is using in a fingerprint mode. It is based on the fact that different structures have different shape, different signatures, I may say, because clearly spectrum looks like signature, and different molecules, different local atomic structures have different signatures. But it is not easy to look to use this method if we would like to extract numerically the local atomic structure parameters from the spectrum. And we, more than 10 years ago, we developed an approach without machine learning algorithm to extract local 3D structure parameters from the analysis of XANES spectrum. And here you could see that when our structure change, is changing, we see the changes also on the shape of the spectrum, and one could follow this both in experiment and in theory. Unfortunately, in opposite to XANES, it is not possible to extract these local 3D structure parameters from from the spectrum using any simple formula. It is not the case. And that is why we have to develop the method for extracting this local 3D local structure information. But the most important problem when you would like to extract a set of local 3D structure parameters from the shape of different type of spectrum or from X-ray diffraction curves, the most important thing that if you don't have very narrow peaks in all your spectrum, it is difficult to be sure that if the solution you found is unique or not. That is why, especially for small nanoparticles, where you also could not extract the precise set of parameters from X-ray diffraction because of Scherer formula, and then also if you would like to analyze XANES spectrum, you have also some troubles here, because if XANES is not very sensitive to chemical bonding, for example, not for distances, but for bonding. And XANES has sensitivity for both distribution of atoms, but important that XANES is sensitive not only to the interatomic distances, but also to bonding angles. But if you would like to be sure 100% that the structural parameters you obtained are correct, and that you find the only solution, then it's better if you could analyze several types of experimental data. But we will now mostly concentrate on XANES data analysis. What are the benefits of machine learning? The most important thing here is that after you train your model, if you have just trained machine learning set, then it could elaborate spectra very fast enough. And in principle, you could do it on the fly. Just directly when you have your experiment, you could analyze the data. And it is important now because now experiments became more difficult, sophisticated equipment. And in many cases, when you return back from large-scale facilities, you spend several months to understand that your data is not good enough. And that is why machine learning could give a solution also for this problem. Previously, approach we are using was organized in such a manner that we tried different set of parameters of local 3D structure, calculate more or less with Benicio approaches, calculate the spectrum and compare with the experiment. If there are any different deviations, then we change the set of parameters and remake calculations. And important that this calculation needs a lot of even supercomputer time, and we need large resources. But when one apply the machine learning method, you spend some time for preparation train set. Then you should train your algorithm, and after this, everything very fast. Also, there are some important things that are not, maybe not trivial. For example, initially we should calculate spectrum on a grid of 3D local structure parameters. And clearly, initially, one could think that the easiest thing is to make calculation on a grid, like on the left hand of the figure. But what you could see, red points is projections where you could see the variation of your parameters. And you could see that you obtain here only 4 red points, mean 4 parameters, but you made calculation for 16 different cases. You spend a lot of time, but the result is not so large scale results. Then there are 2 other more advanced approaches how to make this grid for your simulations. And we found that these 2 possibilities are much better than simple trivial that we have on the left hand of this figure. Then important also step is the choice of the best code for more or less ab initio calculation of the spectrum. Clearly, depending on the type of atom and the type of age, absorption age, you should choose different approaches. But because till now there is the best approaches for simulation of each type of spectrum. And you could see here in this figure that there are several different methods, different codes for simulation of XANES to generate this training set for machine learning. And in this case, it is still important to have a rather qualified person who suggests which of the codes you should use in your own case. Okay, and the training set. We select several sets of parameters and simulate spectra for these sets, and thus having these databases, we could start train our machine learning algorithm to analyze the connection between this set of parameters and this type of spectrum shape. And it is possible to use different type of machine learning. We present here several possible methods, schemes for machine learning, but depending on the size of the training set you obtain, you could select the best choice of these sub methods for machine learning. And if it is difficult for you to simulate spectrum, then you have clearly limited number of, no, let's say points in your training set. Thus, we found that ridge regression or extra trees is good enough. For machine learning, for neural networks, one need more, no, larger training set. Now, also, we would like to mention that there are two more or less opposite type of machine learning. It is direct method or inverse machine learning method. Maybe these names are is still not widely used, but they work with two different approaches for connection the point on the spectrum and the set of machine learning, the set of the set of 3D local structure parameters you have chosen for the to present your molecule or your nanocluster. Well, and we will not explain in more details the methods, but it's better to transfer to the examples, to the case studies where one could understand much better pro and contra of this or another method for the simulation. And at this stage, could we slightly change positions with another Alexander Guda?
Okay. It's unusual talk, so we share. Thank you, Alexander Vladimirovich. We will discuss briefly the case studies existent in the literature first, and then proceed with our own examples. So we should mention the group of Zheng, who started with a more sophisticated fingerprint approach and developed several different metrics between spectra. And then they elaborated dozens of such different metrics to select one appropriate structure out of the materials project dataset according to your experimental spectra. In a later work, they extended their model to the decision trees and predicted some more generalized parameters like the local coordination of your structure. Another group is several publications from Carbone and their group who studied neural networks to predict the local coordination of 3D metals, and they studied several 3D metals in the periodic table, and they found a good quality to predict tetrahedral, octahedral, or square pyramidal coordination of the 3D atom. Moreover, they studied the amount of information in the pre-H or post-H region of spectrum. Group of Timoshenko and Frenkel applied machine learning to the XANES and XAFS regions of spectra to predict shape of nanoparticles and radial distribution function. Finally, we can mention a group of Rankine and Penfold, who applied deep machine learning to predict shape of spectrum and discussed the type of the structural representation for the proper prediction. At this moment, we want to show some of our results and the concept that we try to develop. In the first work, we applied inverse machine learning, where we predicted spectrum for a set of structural parameters and then varied parameters every time to find a good fit for the excited state of the iron terpyridine molecule. we found quite a good agreement, and in general, this is what usually people publish, such a good agreement between theory and experiment. But then question appears, how good is your fit and what are the uncertainties? And having the training set in hand, we can explore the structural space and see the depths of the L2 norm near your best fit point, and see the correlation between parameters using such 2D plots of L2 norm. One can predict directly structural parameters from XANES, but this small molecule with just 3 atoms demonstrates the problem of such approach. If you parameterize your system with 2 different distances, P1 and P2, and you can see that these 2 molecules, they have completely different values of P1 and different values for P2, but XANES will be similar for them. And that's why algorithm becomes a little bit crazy and gives you a very big errors in the prediction. And therefore, for this case, exactly, you should apply another set of structural parameters. The more common is radial distribution function, angular distribution function, which we mentioned on the previous slides from another groups. So our approach is realized in PyFitted software, which is open source, and we are open for collaboration here. So the new area, what we try to develop is a dimensionality reduction of spectra. It's well known that in machine learning, the reduction of dimensionality usually improves your analysis. And many approaches are done for this. And on this slide, we show the reason why you have to apply some additional manipulations with your algorithms to predict properly, analyze properly experimental data. So first of all, we have in XANES especially, we have a lack of standardized database of experimental spectra. Measuring at different synchrotrophs and in different experimental conditions for the same compound, you can get completely different spectra. And even if your experiment is done nicely, your theory is lacking in reproducing high quality experimental features. So it's not like in Rietveld refinement or in XANES, where you can obtain 100% agreement between your ideal model. In XANES, we cannot. Even for metal foil, you will have a big systematic differences. Therefore, it's a good approach to use descriptors of spectra. So not the full spectrum, but some meta parameters of the spectra. And from 80s or from 90s, people already know who used X-ray absorption spectroscopy that positions of minima and maxima depends on the interatomic distances. It's a semi-empirical Natalie rule, and Natalie was the first who used descriptors of spectra. Nowadays, everybody uses Fourier transform XANES analysis to fit first or second coordination shell. So you can fit not the whole structure, but just a part of your structure, and you use descriptor of spectrum. So you use just a certain sign component of your Fourier series of your spectrum. So that's also a descriptor of spectrum. In a more general approach, you can select, there are publications where you can explore the polynomial expansion of the whole spectrum. We try to focus more on intuitively clear descriptors, such as, again, positions of minima and maxima, edge position, and some pre-edge parameters. And these are nicely for graphical representation of your structural information and search for analytical dependencies between your parameters and spectral features. So we demonstrate some results on the training set for iron in different coordination state in the amorphous silica. So we constructed models of 2, 3, 4, 5, and 6 coordinated iron, coordinated by silica tetrahedra, calculated training set for each coordination number, and then tried to explore the features of spectra for each coordination number. And you can plot the descriptors of your training set on the nice scatter plots. For example, here you can plot all positions of your main minima in spectra and the curvature of your white line. So you may see that for 6 coordinated and 5 coordinated species, your white line is very sharp. but for 2 and 3, it's not sharp. And this curvature can help you to discriminate between 6 coordinated or 3 coordinated models of iron. The same you can using just 2 descriptors, curvature of white line and position of H, you can discriminate between different coordination numbers. Another descriptors, H energy and the minimum energy, can help you to discriminate the structures with different interatomic distances between iron and oxygen. More sophisticated descriptors rely on principal components of the data set. So we use here so-called relative principal components after aligning all spectra according to the H position. And you see that structures with small interatomic distances, they are clearly separated. So these are red points on this map. They are clearly separated from the blue points. These correspond to structures with a large interatomic distances. And the same for valence. And what is interesting, you can explore, you can explore the analytical relations between your descriptors and the structural parameters. And for example, here you see that coordination number, after you normalize all your descriptor, you can calculate coordination number in your structure just using H energy multiplied by 0.6 minus curvature of the white line multiplied by 0.56. So it's like a Natalie rule, but now composed of all descriptors. So you can invent many different descriptors and find analytical dependencies. And sometimes it's helpful for the fast analysis. We found several works in the literature who try to find these analytical relations for a certain subset for uranium complexes and some others. And we know the precision, the R2 score, how good we are in analysis. And just a short example on another system, it's a Phillips catalyst. It's a chromium in a it's chromium in amorphous silica now, not iron, but chromium. And with the group of Christopher Copperet, they developed a very nice data set of molecular complexes and measured reference spectra. For them, we extended their data set with theoretical calculations. And again, using descriptors of the pre-H, you can nicely discriminate between chromium in oxidation state 2, oxidation state 3, 4, 5, 6. And you can try to explore the interatomic distances and, for example, number of alkyl bonds in your structure. At this moment, we go to the conclusions and outlook of the work and want to underline the following. So the advantages of machine learning is that you make once recalculated training set using supercomputer, for example, and use it for different experiments on your local PC. You can do on-fly data analysis, as was mentioned in the beginning of the talk, for your very sophisticated and difficult experiments that you do on synchrotron or X-ray free electron lasers. And finally, we can probe the whole space of structural parameters to explore the uncertainties in the field. There are also problems in practical application of these algorithms. These are systematic differences between theory and experiment. They need to calculate new training sets for another classes of objects when you change, for example, ligand type, oxygen to sulfur. And the problem of multivaluedness, so that if your structure is quite symmetrical and you want to predict not cleverly selected structural parameters, your algorithm can fail. Though several works in optical spectroscopy, we found they use tandem neural networks to avoid this multivaluedness, but we never tried this for the XANES spectra. There was a big group who contributed to this talk. Some people are mentioned on this slide, and we are welcome you to ask questions.
Okay, well, cheers to both Alexanders for that talk. It's really good all round, and yeah, I certainly enjoyed it a lot. We haven't got any questions in the questions and answers yet, but feel free to drop them in there as soon as you have them. I mean, of course, I have a question straight away. I think what you've done here is really cool, and what I'd like to know is, with your choice of descriptors for your spectra, I guess at the minute you're choosing those, is that manually, or is there essentially the potential that you could use perhaps another neural network or another machine learning model to extract the descriptors from the spectra in the first place before feeding that onto your second model?
Yeah, actually, it's a very good question. We asked one student from a mathematical department. So we had an idea that neural network can construct such descriptors that are better correlated with the structural parameters. So we made a very big training set, and we know some structural parameters for each item in the training set. And then we try to train neural network that finds such descriptors, so the distance between these descriptors correlates proportionally with the distance between structural parameters. So this work did not converge to something good at the moment. Therefore, we most selected on these descriptors of the spectrum that you do. Yeah, it's just algorithm that searches minima and maxima and does it for the whole data set for your thousands of spectra. And then we try to combine several of them and check on the quality. And I would say we more or less always have a good quality for classification of a single property, but there is also a very big set of problems related to the mixtures. And actually, when you have a mixture, you have a trouble because your descriptors, they start mixing, and you have to do cross-validation on your mixture data set, but not on the pure component data set. So this is what we also try to address.
But also we could think to train network to write nice papers for Nature or Science. We are thinking about as well.
Of course, that's got to be the next step, I think, for
Yes.
for all of us. It would help the community a huge amount.
For researchers.
Actually, I had a quick question on the convert from the spectra to structure. When you have how general, so you showed for these iron with the silicates. So how much does it work outside this? Can you apply this to an iron in a completely different environment, or is it kind of that class dependent?
Yeah, so now we applied it mainly to the iron in silica, and we extending the training set with more parameters. So we found that we lack some tilt angles and some distance distribution for fitting the real catalyst. So we applied it first to some geological samples, but then we got the data from our colleagues about the iron catalyst in silica, dispersed in silica, and we found that this training set didn't work well. So we extended it with some structural deformations. We didn't try it for another ligands, but for just oxides, geology samples, and after extension, it worked good also for catalyst. For sulfur bonds, for sure, it will not work. Or also for carbides will not work. So mostly oxygen environment. Second coordination sphere may be slightly different. So iron, oxygen, silicon, and iron, oxygen, iron, more or less you can predict some general trends. Although iron, oxygen, iron will give you quite a big impact on your shape, but some general features you can predict. So oxidation state, still a good quality that we apply the cross-validation on the oxide system.
But we also, mostly we are limited to the nice sets of experimental data, and that is why we are looking for collaboration. And if you have any ideas or any proposal, we are open to start working with this. Thank you.
Okay, we've just got another question in the chat. This one from Diego. So I'm just going to read this one out for you guys. So this is a great method to get the structure for unknown systems. But what happens if the unknown system is a mixture of two phases? Would the machine learning code give fractional coordination numbers? And if not, do you have ideas on how to deal with mixed systems in the future?
Yeah, so this is what we discussed in the end. You can predict the average coordination number and average valence. And importantly, you have to train your algorithm. So you calculate the pure compound, but then you train your algorithm on the mixtures. And if you evaluate descriptors, you have to evaluate descriptor for the mixture, linear combinations of your spectra. And for now, we have around 1,000 of the entries, of the single component entries. And then you have to prepare at least 10,000 or better, several 10,000 of the mixtures to train your algorithm properly. And then you have to do cross-validation on the mixtures to find the proper set of descriptors for a good prediction quality. So, and we found that one subset of descriptors, you select 5 descriptors or 4 descriptors, they were good for a classification problem on a single compound. You can clearly distinguish between 3-coordinated and 4-coordinated, but the same set does not work for mixtures because the descriptors can mix and they fail. And for prediction, so you can easily predict average values, but also you can predict the entries in the mixture. So you can, you should just think a little bit to make it more or less unambiguous. For example, you can predict the oxidation state of a major component or coordination number of the component with the highest concentration. This is all possible for sure. The more things you try to predict, the more uncertainty you get.
Right, thank you.
There is one question in the chat as well, Connor.
Yes, there is. Yeah, just about to go on to that one. So from Francesco, also thanks for the really nice presentation there. Francesco was wondering if you include or intend to include the relative stability energies of the generated structures in the selection of the structural parameters.
Relative stability energies. Yes, currently we don't do this, but I know there is, for example, USPEX software to predict some structures using evolutionary algorithm, and it uses to select the best structure the enthalpy value. And one can combine USPEX with its enthalpy values with the XANES L2 norm of to your reference experiment data. So in principle, this is a good thing to combine DFT predicted models with L2 norm of XANES and do some global fit of your models. But in practice, we don't have a worked example of such approach.
Okay, yeah, that makes sense. I suppose it's almost like there's been a lot of development in this area in sort of in machine learning, and it's almost a case of putting multiple things together to form some kind of data pipeline in a sense. You know, perhaps if you're predicting the structures and then it's then put into another system that's able to discriminate in this way, you know, perhaps that's the way forward. Who knows? But yeah, in any case, thanks for the talk again. I'm sure I speak on everyone's behalf when I say it's a really nice piece of work there. And
thank you for invitation.
No worries. And I think that concludes the talks for the day. Just leaves us for the poster session and the drinks reception, which I don't know how that will be done virtually. But
well, so yeah, the posters we provide, the drinks you provide yourself.
That sounds like a bad deal to me. It should definitely be
the downside of a virtual event. But yeah, just what